Your last podcast of the semester has to do with dimensional analysis.
Which, as it sounds, is analyzing things
Dimensionally. You may have actually done this in one of your math classes. There's a little bit of overlap, but I don't know which one, so see if it looks familiar. This is a skill we're going to be using a lot during the year, especially after the semester exam in the next chapter.
So basically what we're doing with dimensional analysis is using equivalent statements, which can be set up as ratios, but an equivalent statement really just shows a relationship between two units.
So, for example, this is a definition, if you will. Those are equivalent statements. We know that in every 1 inch, there are exactly 2.54 centimeters.
Hey, reminder, sig figs, infinite number of sig figs in there, because that's a definition.
That's a definition, so that's good to know. So definitions we don't have to worry about the sig figs because they're infinite. But this is just a conversion. Most of the time you do this in your head or on a calculator, but we're going to show you how to do it mathematically, because in the next unit you will not be able to do them in your head. They're going to be really complex. So it's very important. We're more worried about the setup than the actual answers for some of these.
Yeah, so really the gist of what we're getting at here is a system to solve relatively long mathematical problems.
And we're going to show you with very easy mathematical problems. So here's an example of a conversion factor as a ratio. When we say there are 3 feet in 1 yard, this is a conversion. We can set it up as a ratio 1 over the other. For every 3 feet, there is a yard. Those things are equal.
And I would hope you'd agree that 1 yard over 3 feet is essentially the same statement, just in the opposite way.
We put one over the other as a ratio. And sometimes you put it one way, sometimes you put it the other. Let's figure out how to do that. First, we're going to look at the metric system. And we didn't put all the metric system in here. Your book definitely has more, but these are the most common ones that you need to know the definitions of, because the metric system really just gives us a list of common conversion factors. We compare everything in the metric system to our base unit. If we're in volume, we talk about liters. Mass, we have grams. If we're in length or distance, we use the M, which stands for meters.
Meters.
It's meters. If we have anything else in there, seconds, we can do that. And then the units just go with those. For instance, if we have grams, we could say kilograms. We could say megagrams or gigagrams. We don't use that very often.
You usually hear that more with computers and gigabytes.
Ooh, gigabytes? Are those compared to regular bytes? They are.
Like if you want to take a really big bite of your sandwich, you take a gigabyte.
That'd be 1 billion bytes. No, well, a gigabyte would be 1 million bytes if you were talking about chewing. But bytes are computer language. You can have kilobytes, megabytes, gigabytes. They're all compared to the base unit, a byte. These definitions are very common. Kilo means 1,000 times bigger. So pay attention. That's 1,000 times bigger than the base unit. That means you need 1,000 of the base unit for 1 kilo. So
So the kilo unit is a big unit. The base unit is a smaller unit compared to the kilo. So you don't need as many of the kilograms. You need much more of the
smaller unit.
Grams.
So since kilo is bigger, I need fewer of them. 1 kilogram is going to be equal to 1,000 base units. 1,000 regular grams. That's how it works. 1,000 kilograms does not equal 1 gram. That's backwards. So knowing how to read the chart makes sense too. On the lower side, we have these. Deci is 1/10. Centi is 100. Well, now it's smaller. I need more of my smaller ones. So it's going to take 100 smaller ones. Centimeters, for instance, are in 1 regular meter.
All right. You should be familiar with those first 3 at least, right? Deci, centi, milli.
Milli. Micro, this is a weird Greek M. It's kind of a curly, swirly M. Stands for 1 million times smaller, and nano is 1 billion times smaller.
Which actually is pretty common to see in chemistry, but we're not going to really deal with nano stuff that much. But you've probably heard of nanotechnology, and that's what we're talking about, stuff that is really, really small, basically.
This is how big atoms are. They're in the nanoscale. These you're going to be expected to know to help you with certain conversions. These will not be given on tests, but you do need to know them. All right, so we'll start out with some simple practice using the metric system and other things. 1.45 meters to kilometers. The important thing here is to find a number that you know, that you're given, and find that as your starting point, 1.45 meters. I want to know how many kilometers that's going to be equal. So I need to convert meters to kilometers. I think everybody can do that if you know that a kilometer is 1,000 meters in your calculator. So, but let's set up, we're not going to set up a ratio, we're going to set up dimensional analysis unit conversions.
So when we do this, we're going to start with 1.45
meters.
And we're basically going to put it on the top of a fraction.
Okay. So that's a whole number. We're just going to, we have one over 1. There's
Yeah.
no units on the bottom, but we're going to treat it as a whole number because all the other conversion factors are fractions. So we're going to set up this chart to help us do these conversions. What's the relationship between meters and kilometers? Do you remember from the last slide?
There's 1,000 kilometers in a meter, right?
No, meters is smaller, so we need
right.
more of the smaller one. 1,000 meters
1,000
is
meters is
1
kilometer.
kilometer. Well, now, these are 2 fractions. So we're going to treat this just like you were multiplying 2 fractions. If this were 1.45 meters over 1 times 1, that should say kilometers, over 1,000 meters. How do you solve this problem when it looks like this? Well, you multiply all the numerators together, you divide by all the denominators. So this bracket is really just a series of fractions put together. That is going to help us later on when we set up these brackets. So 1.45 times 1 divided by 1 times 1,000. So divided by 1,000. And we get 0.00145 kilometers. Now the reason we get that, usually we ignore the fact that we started in meters and we had kilometers. Why does that work? Well, what happens in a fraction when you have x over x?
You get 1.
Because they cancel out.
Yeah.
So those both cancel out. Same thing with units. This is like doing algebra with units. We have meters in the numerator and meters in the denominator. They cancel each other out, and we're left with kilometers as our final answer. So the meters, this shows us why we can just move the units from meters to kilometers. It's because we converted them and we canceled out the units. Yards to centimeters. Well, we don't have that conversion factor in the metric system, but what do we have?
We do have a conversion from yards to inches. Oh, you're talking more about the metric system that we know. 2.54 centimeters in 1 inch. We did show that earlier in another slide.
Not yet, actually. We're going to show it in the next slide.
No, it was in another one. It was earlier. And it's going to be in the next one.
I don't think it was
It was in
earlier.
both.
We'll have this debate afterwards. You guys all know that I'm right now
Right
because it's not up there. So this conversion here, this is not in the metric system. We would give this to you. Centimeters to inches. So let's use that. I've got 2.5 yards, and I want to know how many inches that equals. But this conversion, I want to know how many centimeters that equals. This conversion only gives me centimeters to inches. So I can't do this one in one step.
Yeah, so you were thinking ahead there. We do need to convert the yards to inches. That's really what we need to get to. And then we can get from inches to centimeters because we know that conversion
Because
factor.
we have this one.
Yeah. But most of us hopefully know how many feet are in a yard.
Okay.
And how many inches are in a foot.
How many inches are in a foot. So
Yeah.
you can use other conversions that you know to help you with these problems. If I start with yards, since my units need to cancel out, here's how you set this up. Once you set up this, we call it a T-chart. Whatever units you have here, they need to go in the bottom over here because we want them to cancel out. We want those yards gone. Since we're trying to get to centimeters, we know that we can get there through inches. So yards to inches. Well, that's related by feet. 1 yard is 3 feet. And now I'm going to set up another T-chart right next to it.
So yeah, we can go from inches to feet, or sorry, feet to inches. We don't want to go the other way around.
So 1 foot is 12 inches. The feet cancel out. And now I'm in inches, so I can use this conversion right here to go from inches to centimeters. Yep. 1 inch is 2.54 centimeters. Inches over inches cancel out. And then what are we left with? Well, now we're essentially left with 4 fractions. 2.5 times 3 times 12 times 2.54.
This one works out nice because there's all ones on the bottom, so we don't have to divide by anything.
All the denominators are 1. So if we multiply all the numerators together, we get 228.6 centimeters. That's the only unit left that does not cancel out.
Now, this is the number straight out of the calculator.
This is what the calculator gives you. But remember, now we're in chemistry, we have to be smarter than our calculator.
And we started out this problem with a measurement, 2.50 yards.
This value right here is a measurement. So that means it has sig figs. How many?
It looks like it has 3.
We started this problem with 3 sig figs. These are definitions. Here, the 12 inches in a foot, 2.54 centimeters in an inch. Those are all definitions. Those don't matter because they're infinite. So since this is really all multiplication and division, our multiplication division rule says the least number of sig figs.
So we got to round our answer to 3 sig figs.
To 3, because we started with 3.
Yeah.
With all of these problems, you really just look at what you start with. If you start with 3, you should end with 3.
Okay.
Because you're using conversions in the middle, and those don't matter.
So we look at that number, the 228.6. 2, 2, and 8 are our first 3 sig figs. So that 6 makes the 8 round up to a 9, and we have 229 centimeters. Is there actually 229 centimeters in 2.50 yards? Not quite.
It's an estimate it's rounded based on how accurate our initial estimate was. So this is why we do sig figs. Your calculator gives you one answer, you have to round it to another, and you have to figure out how. Inches to meters. All right, well let's hurry through this one. We've got inches. We start out with that, and we're going to put it over 1.
And we know our conversion factor from inches to centimeters, and we know one from centimeters to meters as well. So we're going to start off with that inches to centimeters conversion.
Oh, see what I started to do there? I put 2.54 centimeters on the bottom, but these units didn't match.
Nope.
So
the math's not going to work out here.
Inches and centimeters won't cancel out, so I need to erase those and start again. Since I have inches on top, we need inches on the bottom. So 1 inch is 2.54 centimeters.
And then there are 100 centimeters in 1 meter.
And this is one that you just need to know. You need to recognize that you have the metric system at your disposal.
So really, we're doing 7 times 2.54
divided by
100.
So 3 fractions here. You multiply all the numerators, divide by the denominators. Plug that into your calculator and you get 0.1778 meters because the inches are gone.
Round that using our significant figure rules. The 7 number we start with has 3 sig figs. The number we have as an answer has 4 in it, so that needs to be rounded off.
178. That's our third sig fig.
Awesome.
The 8 rounds the 7 up. Meters. This rounded answer is the correct one. Okay.
Now it's time for my favorite part of the podcast. The crazy practice.
It is crazy because now
it's crazy long.
Crazy long. Usain Bolt.
Crazy fast.
He's a very crazy fast man. He ran the 100-meter dash in 9.79 seconds. World record.
Give or take a hundredth of a
Crazy
second there.
seconds. Yeah, I'm not gonna lie. We didn't look that up. We thought it was that, and we might be wrong. So we're gonna convert that to miles per hour. What's hard about this?
2 conversions, it looks like. Meters to miles.
And seconds to hours. We almost had that coordinated on the second one.
That was close.
So
This is not rehearsed.
we are gonna do both of those at once. I've got 100, and that's an exact number. There's a decimal place there. 3 sig figs.
He ran exactly 100 meters, right?
Exactly 100
No more,
meters.
no less. At least he should have on the track.
Well, I should say not exact, because it's around. It's a measurement. It's about
precisely. He ran precisely 100 meters.
9.79 seconds. Okay.
Very quick.
Centimeters to inches. So we need to get to centimeters so we can get to miles, because miles is related to the English system. So 1 meter is 100 centimeters.
Okay. Looks like a good start.
Meters are gone. What about the seconds? Well,
we're going to ignore those actually for a little bit.
Ignore it. We'll come back to seconds.
We're just going to convert the meters first.
Notice
into miles.
Notice this is a fraction. This one's not over 1 now. There's a division sign there. So we put 100 meters over 9.77 seconds. 9.79 seconds. If we had miles per hour, it would be miles per 1 hour, and we would put 1 hour on the bottom, just like this one is. There's an implied 1 there. Okay, centimeters. 2.54 centimeters is 1 inch.
There are 12 inches in 1 foot.
Now, why did you do that? Why did we go to feet?
Well, because just off the top of my head, I remember how many feet are in a mile.
Oh, okay.
That was just one of those things I remember from
5,280
6th grade math.
feet in 1 mile. So that, again, there's another conversion that we're familiar with that will help us get there. So feet to miles. Well, I have miles. That's what I wanted. So miles, check.
Cool. So we're done the problem, right?
We are not, because look at the units that don't cancel out. We've got miles, and we still have our seconds way back over here.
Yeah.
So seconds to minute, or seconds to hours. I think everybody can do that, but what we're going to do is we're just going to tag it onto the end here.
Okay.
They don't need to be next to each other to cancel out. It's all multiplication. If you have something on the top and bottom, they'll still cancel out,
right?
Even if we started on the bottom. So we're going to do like upside down dimensional analysis.
Uh-oh.
Crazy.
It does sound
upside
crazy.
down and far apart
Again,
dimensional
why
analysis.
this is crazy practice.
Crazy practice. Seconds is on the bottom. So
we
way
need
over
seconds
here,
on the top.
I want seconds on the top.
How many seconds are in an hour?
I don't know, but I know seconds to minutes.
Oh. And do you know minutes to hours?
60 seconds is a minute. I do know minutes to hours, actually.
Perfect, then we're there.
I'm glad I learned that one.
Yeah.
So seconds, even though they're really far apart, the seconds will cancel out. Now minutes is on the bottom. I want to cancel that out, so I have minutes, and I can go to hours. What's the conversion? 60 minutes is an hour. Minutes are gone, upside down.
So now it looks like the only units we have left in this problem are miles and hours.
So when we do
and
all
that's
of
what
this,
we want our answer to be in.
Yeah, these didn't cancel out. So when we do all of this math, the number we're left with will be hours. Miles over hours. Miles divided by hours. We plug all of this into your calculator, all the numerators together, divide by all the denominators. Yes, a problem like this will probably be on your test. You get an answer of 0. Just kidding.
He's not that slow.
He's not that slow. 22.8 miles per hour, per 1 hour.
Put that in perspective. The T-Rex apparently, well, supposedly, I don't know if anybody really knows this because no one's really seen one, ran about 35 miles per hour. And that was a gigantic creature. I guess that would make him slow.
22.8 miles per hour.
fast.
That's crazy fast.
Yeah.
He would be speeding in a school zone.
Nice.
But sig fig wise, let's take a look and see what that comes out to be. Sig figs, we look back here for sig figs.
So we're really just looking at our 2 numbers that we started with, the 100
There's
and the
3 there.
9.79 seconds, because those are both measurements. We measured off 100 meters for him to run, and then he ran it in 9.79 seconds.
Each of those has 3 sig figs. My answer has 3 sig figs. We don't need to round it.
So again, all the conversion factors, not significant. The beauty of dimensional analysis, when you write the units, you can see all the units cancel out, and you can check your work immediately.
If they don't cancel out, you got it wrong. Wow, that was crazy long.
Indeed.